Okay, we're back. The third section of this week's homework, which is cross-sections. Okay, there's this worksheet called volume by cross-sections, or volume by slices, some people say. And I wanted you to do 5 problems from this. Actually, some of this I kind of did in the video. So here we go. We're going to do this really fast. 2b said the solid, there's some solid, which lies between planes perpendicular to the x-axis at x equals 0 and x equals 4. Cross-sections perpendicular to the x-axis between these planes run from y equals negative x to y equals x. So, okay, so from y equals negative x to y equals negative root x to y equals root x, they say. Okay, well, that's kind of an awkward way. Oh, and specifically they say between x equals 0 and x equals 4. So really, they might as well just be describing the parabola x equals y squared. And so I'm going to read this problem several times because I think reading it is half of it. What's going on again? The solid lies between, and I think it's helpful here to sort of think about this as 3D, although I'm not going to draw 3D because I don't have the skill. And also there's a picture on the paper. The solid lies between planes perpendicular to the x-axis. Well, that's the x-axis, so this is a plane perpendicular to the x-axis. It lies between planes perpendicular to the x-axis at x equals 0 and x equals 4. So whatever else this shape is doing, it lies between x equals 0 and x equals 4. Cross-sections perpendicular to the x-axis. So in other words, we're cutting it like this. Between these planes run from y equals root x to y equals negative root x. Okay, so after all that sort of weird language, I think I realize what's going on here, which is that we're going to build a solid whose base, this is what I referred to in the video as the real estate that we have purchased on the ground, is just this one. It's the region enclosed by the parabola x equals y squared and the line x equals 4. And now we're ready to begin problem 2, b, which says cross-sections are squares. Well, if cross-sections are squares, then I just have to imagine that for some arbitrary x value between 0 and 4, I have some, I guess I can call it a rectangle, but it's really more of just a line or something like that. And what is the length of that line? Well, from here to here is root x, and from here to here is another root x, and so the length of that line will be 2 root x. And what we're going to do is we're going to build a solid such that at any given point along the x-axis from 0 to 4, the shape coming out is a square. And it's a square whose dimensions are determined by using up all of the real estate that we have. Okay, and therefore the way to do this problem 2b is to say, okay, let me take the length of that red line, which is 2 root x, let me square it. Now that gives the area of the square, which is coming out of the board, multiplied by dx gives me the volume of that infinitely thin square, and then I just add them all up from 0 to 4. So la 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 la, and square, and dx, and 0 to 4. Yeah, that's it. Okay, and now this I think is just easy to do because we just get 4 integral from 0 to 4 of just x. Yeah, and okay, so that's 4 times x squared over 2, evaluated at 4 and 0. So that's going to be 2x squared, evaluated at 4 and 0. So that's going to be 32. For some reason I'm doubting myself that it would be so big, but maybe that's just right. Is that, let me just double check everything. Y equals 2 root x. I don't have an answer key to this, but this seems good. For arbitrary x value, that's 2 root x square coming out of the board, dx, integrating 4x seems just good to me. 16 times 32. Yeah, so if you want to think about it like this, if you were to go from, so this point is like 4, negative 2, and this point up here is 4, 2, right? So if you were to make a cube enclosed by this, so like enclose this whole thing in a 4 by 4 cube, this shape is filling up precisely half of that cube. And I have no idea whether that's a reasonable answer or not, but there it is. Okay, 2D is just a follow-up on the exact same problem. 2D now says, okay, cross sections are equilateral triangles with bases in the xy plane. So it's the exact same problem, and I'll use the same picture and everything. But now I build, instead of squares coming out of the board, equilateral triangles coming out of the board, whose side lengths are determined by the length of that red line. Alright, so we've previously proved that if you have an equilateral triangle with side length s, that the area of that equilateral triangle is s squared root 3 over 4. That's just like a math fact. And therefore, I take that 2 root x and I square it times root 3 over 4. That represents the area of an equilateral triangle whose side length is that red line. And then I multiply by dx and I integrate from 0 to 4. Notice that this integral, I don't actually have to waste time doing it, because this integral is going to be precisely root 3 over 4 times as much as the old integral, because that's just a fact. And so the answer to this problem is just going to be 8 root 3. Okay, 2 down, more to go. Number 4. Let's see, can I just fit this right here? Maybe. 4 says, the solid lies between planes perpendicular to the x-axis at x equals -1 and x equals 1. Cross sections perpendicular to the x-axis are circular discs whose diameters run from the parabola y equals... Let me just make some space. Seems better. Okay, so here we go. Number 4. What's going on? We have y equals x squared, and we have y equals 2 minus x squared. The language of this worksheet I think is a little bit confusing, but it runs from one parabola to the other. Okay, let's graph these two parabolas. Well, first of all, where do these two parabolas intersect? When is x squared equal to 2 minus x squared? Answer when 2x squared minus 2 is 0. So that's, okay, this is just kind of stupid. This is when x is plus or minus 1. So when I go to graph this, 1, 2, so here's 1, and then when I plug in -1, I also get 1. So what am I doing? I have this parabola y equals x squared, but then I also have the parabola 2 minus x squared, so it looks like that, something like that. Okay, so yeah, there is my, this is kind of boring, actually. There's my shape. It's, or what I called in the video, the real estate. It's the area enclosed by the parabola y equals 2 minus x squared on the top and y equals x squared on the bottom. Okay, and what are we doing? We are building a solid. What can I say about this solid? Well, the solid lies between planes perpendicular to the x-axis. So this is the x-axis, so this is a plane perpendicular to the x-axis. It lies between planes perpendicular to the x-axis at x equals -1 and x equals 1. That's just another way of saying this whole shape is contained within this plane and this plane. And of course this is the point 1, comma 1, and this is the point -1, comma 1. Okay, and what can I say about this shape? Cross sections are circular discs whose diameters run from this parabola. Okay, in other words, this is not a solid of rotation, but it is a solid whose cross sections are all circles or circular discs. So given a particular representative rectangle now, and I can tell you precisely what the length of that representative rectangle is going to be the difference between the y-coordinate of the top parabola and the y-coordinate of the bottom parabola. So it's going to be 2 minus x squared minus x squared. So it's going to be 2 minus 2x squared. Okay. And what do I do with that? I let that length be the diameter of a circle, which is going sort of under and above this thing. Okay, so how do I do it? I take that length, that 2 minus 2x squared thing, that represents the diameter. So if I now divide that by 2, that represents now the radius. And if I pi r square it, that represents the area of the circle, and I multiply by dx to give it some thickness. Now this represents the volume of one circular disc coming out of and going underneath the board, whose diameter is equal to the length of that red line. That's what we're doing. And then we add them all up from -1 to 1. Okay, a couple things going on here. First of all, both these functions are even, so I can save some time by just going from 0 to 1 and multiplying by 2. So I'll do that. And then, let's see, this simplifies to 1 minus x squared. So now it's just this integral to do. So that's 2 pi, 0 to 1, 1 minus 2x squared plus x to the 4th. And that's x to the 5th over 5 minus 2x cubed over 3 plus x. And that's all happening at 1 and 0 with a 2 pi on the outside. So what's this? Oh man, might have run out of space here. Let's see. 1/5 minus 2/3 plus 1. So putting that all into 15ths gives me 3 minus 10 plus 5. So 3 minus 10 plus 5. No, plus 15. 15th. That's 2/15. So 2 pi times 2. No, sorry. What's happened? 2/3 is 10/15, 1/5 is 3/15, and 1 is 15/15. So 15 minus 10 is 8/15. So I guess this is 16 pi over 15. I bet that's maybe right. 18. No, sorry. Yeah, 8/15 times 2 pi, 16/15. Okay, good. 2 more to go. Well, not more than 2 more to go, but okay, we'll see how this goes. 7a. The base of a solid is the region between the curve y equals 2 root sine x. So 2 root sine x. And the interval 0 pi and the x-axis. The cross sections, we're doing 7a. Okay, so what does 2 root sine x look like? I don't know, man. It's going to from 0 to pi. Well, sine of pi is still 0. That's still 0. At pi over 2, it's still going to be, sine of pi over 2 will be 1, so the square root of 1 is 1, but now everything's being stretched out by a factor of 2. So in some ways you might think it doesn't look that much different from sine itself, but we're taking the square root of it. Well, when you take the square root of a number that's less than 1, it makes it bigger. So this is going to be kind of like a fatter sine, I guess. So something like that. Anyway, here is the region, and what am I doing with this region again? I am building something. What am I building? A solid such that cross sections perpendicular to the x-axis are equilateral triangles. So once again, I just draw my representative rectangle and I say, okay, what is the height of that representative rectangle? Answer, it's 2 root sine x. And now I want an equilateral triangle. Well, I just now know that an equilateral triangle's area is s squared root 3 over 4. So that becomes the area of the triangle coming out of this board, whose side length is equal to that red line. I multiply by dx, and I integrate from 0 to pi. And I think this just works out really kind of boring, right? You square the 2, you get a 4 that cancels that. And so this whole thing just becomes root 3 integral from 0 to pi of sine All right, and I just know from like knowledge that this integral is just 2. The integral from 0 to pi sine is just 2. So this whole thing is just going to be 2 root 3. Okay, good. One more and then more. 9. This one's interesting because you have to read a lot and it's harder. Here's what it says. The solid lies between planes perpendicular to the y-axis at y equals 0 and y equals 2. The cross-sections perpendicular to the y-axis are circular disks with diameters running from the y-axis to the parabola x equals root 5 y squared. Alright, I didn't get any of that, so I better just start at the end, which is I have some x equals root 5 y squared curve. Let's try to understand that first of all. Well, I guess that I can do. That I can do. It's just going to be a standard kind of parabola type thing. So, you know, something like this, but stretched out kind of weirdly. Okay. Maybe now I'll try to read this problem again now that I have at least a shape. Here's what it says. The solid lies between planes perpendicular to the y-axis. Aha, that's the y-axis. This is a plane perpendicular to the y-axis. Y equals 0 and y equals 2. Okay, well that means that this entire shape is going to live between the y equals 0 and y equals 2. Alright, well when y equals 2, x is 4 root 5. Alright, so what I have is something like this. I have some sort of point. This point is apparently 4 root 5, comma 2. I guess. No, I guess I have that backwards. No, that's right. When y is 2, x is 4 root 5. So yeah, when y is 2, x is 4 root 5. And so, so this whole shape is going to live between here and here. Let's read more carefully again. The solid lies between planes perpendicular to the y-axis at y equals 0 and y equals 2. Cross sections perpendicular to the y-axis. Okay, so they're describing what happens when I slice this solid perpendicular to the y-axis, are circular disks with diameters running from the y-axis to the parabola. Aha! Only now on my third or fourth reading do I realize that the base of my region lies in the xy plane. The base is this region, and when I draw my representative rectangle, I draw it running from the y-axis to the parabola. So now I'm given an arbitrary y value, and I have to say what the equation or what the length of that rectangle is. But here now we have to be a little bit careful, or maybe we don't have to be careful. Because this is the curve x equals root 5 y squared, which means from here to here is just that length, right? It's just going to be root 5 y squared. So that is right? Yeah, because that sort of point, so to speak, for any given for an arbitrary y value, that point will be root 5 y squared comma y. And so the length of that red rectangle will be root 5 y squared. Okay, what am I supposed to do with that again? I'm going to construct circular disks. Okay, so I think if I'm doing this problem correctly, I bet I am. I take this root 5 y squared thing. That represents the diameter. Yeah, so I have to divide by 2 to get the radius. Then I square that and multiply by pi to get the area of the circular disk, which is kind of coming out of the board and going back behind the board, whose diameter is equal to that red rectangle. Then I multiply by dy to give it a little bit of thickness, and then I integrate up the y-axis from 0 to 2. Yeah, so this is maybe not so bad. What do I get? 5 pi over 4 times the integral from 0 to 2 of y to the 4th dy. Double check my arithmetic. Yeah, 5 over 4. Yep. And so I get 5 pi over 4 times y to the 5th over 5 evaluated at 2 and 0. Okay, the 5's cancel, and then that's just, so this just whole thing just becomes 8 pi. Because 32 over 8, yeah. Woo! Okay, that finishes the worksheet. Now we have two more problems left from the textbook, and I think I said like don't do them, right? I said like just set them up. Okay, great. So we're going to do 61 and 63, and then we're going to be done with this part, at least. Okay, so 61. I'm going to put this thing down. What are we doing? 61 says, find the volume of the solid whose base is bounded by the graph of y equals x plus 1 and y equals x squared minus 1. With the indicated cross sections taken perpendicular to the x-axis. Okay, I certainly know how to graph this line, this parabola. Where do they intersect? Let's find that now. So this becomes x squared plus, x squared minus x and then minus 2. So I guess that's just x minus 2, x plus 1. So the answer is at x equals 2 and negative 1. So when x is negative 1, y is 0, and the other point is going to be 2, 3. Okay, that means I can make a detailed graph of this. So here's negative 1, 0, and here is 2, 3. Cha. 2, 3. And, okay, x squared minus 1, I see what's going on now. So we have this parabola, and then we have this line, y equals x plus 1. Okay, sure. Okay, so, great. Using my basic skills, I have now figured out the region under discussion. It's the region bounded by the parabola on this line. It's another one of these parabolic segments. And this here is negative 1, 0. Okay, what am I supposed to be doing with this region again? Find the volume of the solid whose base is this region, and such that cross-sections are squares and cross-sections are rectangles of height 1. Okay, so what I now need to do is to draw a representative rectangle and just give the length of that representative rectangle in terms of x. And the answer is that this representative rectangle is line minus parabola. So x plus 1 minus x squared minus 1. In other words, it's x minus, in other words, it's negative x squared plus x plus 2. Okay. So, if that's the length of this thing, yeah, that's just right, then what are we doing in part A? In part A, cross sections are squares. So the squares are coming out of the board, and every square is going to have side length negative x squared plus x plus 2. So I take that side length, I square it to get the area of that square, I multiply it by dx to give it the thickness, that's the volume of one of these infinitely thin slices, and then I just integrate up the x-axis from negative 1 to 2. That's it. That's all we have to do for that problem. Part B says that now cross-sections should be rectangles of height 1. Okay, so now the solid's height is always just going to be 1. Well, this is actually like a little bit silly because the volume of the solid is simply going to be the area of this region times 1. Because the volume is just going to be, it's just going to be a parabola just up. It's just going to be a parabolic prism. But anyway, thinking about it in a multiple step problem, I just take negative x squared plus x plus 2, which is the length of the red line, and I multiply it by 1, so to speak. that gives me the volume of the rectangle, that gives me the area of the rectangle, which has that length, but which is coming out of the board 1 unit high. And then I multiply by dx, and then I add them all up from -1 to 2. But of course that's also just equal to, as I just said, the area of that green region, which should intuitively be the volume of the shape we're talking about, because the shape just comes out of the board by 1. Okay, now actually one problem left, 63, but I think it also has multiple parts. 63 says, 4 parts, oh man. The base of a solid is bounded by y equals x cubed, y equals 0, x equals 1. Y equals x cubed, y equals 0, x equals 1. Find the volume of the solid for each of the following cross sections taken perpendicular to the y-axis. Okay, so that's actually kind of important. So here we go. Here's y equals x cubed. That is 1, 1. And so the curve is going to look something like that. But bounded by y equals 0, x equals 1, and y equals x cubed. So the region under discussion is certainly this one. That's very clear. And what are we supposed to be doing again? By the volume of the region of the one cross. Okay. So now, so I think this is the one which is kind of a little bit hard, right? Because now, drawing a representative rectangle like this, what is the length of that representative rectangle? It's certainly true that if you take y equals x cubed, y equals 2, and x equals 1, then it's the green region under discussion. So that must be the base of the solid. So if this is y, because the other important thing was that taken perpendicular to the y-axis. So cross sections taken perpendicular to the y-axis. That's just what the problem says. So are determined by this region. So okay. So what is I have to find out once and for all what is the length of that red line, and the length of that red line is. We have to be kind of careful, because if this is y equals x cubed. If this is the curve y equals x cubed, then it should possibly be written as x equals cube root y is also a name for the same curve. And that means that this point right here is, this purple point here is going to be cube root y comma y. Which is to say that the length of this red thing is, for an arbitrary y value on the y-axis, the length of this red thing is 1 minus cube root y. So I think that's kind of hard, and you could potentially mess that up in multiple places. Okay, so part A says probably like squares or something, right? Cross sections are squares. Okay, well if cross sections are squares, then I simply take this 1 minus cube root y length, that's the length of the red rectangle, I square it to give the area of the rectangle which is coming out of the board that has that red thing as a side length. I multiply by dy to give it some thickness, and I integrate all of them up the y-axis from 0 to 1. Okay, and I said don't do the integral, so just set it up. Good. Part B, how about if there are semicircles? Okay, well if there are now semicircles coming out of the board, I expect that means semicircles, I think the only way that could make sense is if this is the diameter. So if there's semicircles, some people will say semicircles whose diameter is in the xy plane. Good. Well then, what should I do? I should take this 1 minus cube root y thing, which is to be my diameter. I should divide by 2 to get the radius. That's the radius. Then I pi r square that radius. That gives me the area of the circle with that as my diameter. But then I have to divide by 2 because I only want the semicircle. And that will give me the area of a semicircle with that quantity as my diameter. Now I multiply by dy, that gives me the volume of one of these thin semicircular slices, and then I integrate up the y-axis from 0 to 1. Okay, 2 more to go. C says, what if they're equilateral triangles? Okay, well that's just going to be the integral from 0 to 1 of root 3 over 4 times 1 minus cube root y squared dy. We kind of did this one already. Part D I think is quite hard though. Part D says, what if they are semi-ellipses whose heights are twice the length of their bases? Oh man. Semi-ellipses whose heights are twice the length of their bases. Okay, well, in a previous video, we proved the formula for the area of an ellipse. And the answer is, and it was sort of met with a little bit of a shrug of duh, that if that's A0 and that's 0b, then we should think of this ellipse as being just a circle of radius 1, which has area pi, stretched out horizontally by a factor of a and stretched out vertically by a factor of b. And so the area of any ellipse is going to be pi ab. Okay, but these are, here, send her up, I'm done in like a minute. But these are semi-ellipses. So the ellipse is kind of coming out of the board, so half ellipses. And what are the dimensions of these semi-ellipses? Their heights are twice the length of their bases. So I'm going to interpret that as, if the heights are twice the length of their bases, then I think what we mean is a semi-ellipse that looks like this. After all, this is the base, right? Well, if this is the base, and this is twice that, then really this is an ellipse whose major axis is 4 times as long as the minor axis. And so, okay, if we're going to call this base b, which is convenient, then this is like 2b, right? And then, then what's the area of one of these semi-ellipses going to be? I guess there's a couple ways of thinking about this. One is to sort of complete the ellipse, and then to say, well, if that's b, what's the best way to do this? If that's b, then this is like b over 2 or something, and so you've I'm not doing this the right way, but anyway, you sort of take pi times the semi-minor axis is b over 2. The semi-major axis is 2b. But then you also, that would give you the area of the entire ellipse. But then you want to divide that by 2. And so what you get is pi b squared over 2 or something like that. So in other words, if a semi-ellipse has base b, which is really like the minor axis of the ellipse, and the semi-major axis of the ellipse, it's not how they put it, is twice that, then the area of that ellipse will be, I think I'm doing this right, times b squared, yeah, will be pi b squared over 2. Okay, good, because the b in this case is just the length of that red line. So I take 1 minus cube root y, that's b, I square it, multiply by pi over 2, and that is the area of one of these semi-ellipses. Now I multiply by dy, and I integrate up the y-axis from